In this video, we're going to be looking at maximum and minimum values. And today, all we're really going to be doing is taking care of the vocabulary part of this section here. And if you want to look at any additional examples, you can find them in Chapter 3, Section 1 of our textbook. So our goal by the end of this video is to be able to identify local and absolute extrema given a graph. So here I've given you a picture of a function defined on an interval, and you can see the key characteristics where the points are labeled as either absolute or local max and min points. And by the end of the video, you should be able to do this yourself. Now, before we jump into what maximum and minimum values are, let's try to figure out why we want to be studying these values. So we've already seen how we can use the derivative to solve different types of application problems, such as related rates, velocity, or acceleration. But those are not the only applications of the derivative. Some of the most important applications of the derivative involve what we call optimization. And that's where we want to find the best way of doing something. So if you owned a company, you might want to try to find the minimum cost or the maximum profit. And so you would find a function that would represent those different scenarios, and then we can optimize them by finding the maximum and minimum values for those functions. So we're going to be getting to that later. But what we're going to focus in today are what exactly are maximum and minimum values. And we're going to look at it today by just studying a graph. So I think we know that when we're talking about a maximum value, that we're looking for the largest value. And so in terms of a graph, when I want to find the maximum value, I want to try to find the highest point on my graph. And we can see that that's happening at this point 3, 5. Now, the point right here would be the maximum value. But the maximum value is actually just the y-coordinate of that point. So the maximum value here would be 5. Or we could use function notation to show where it occurs and what the value is. So we can say the maximum value for this function would occur at f of 3, and it equals 5. Similarly, a minimum value would be where we're looking at the lowest point on our graph. And in this case, our minimum value would be at this point. And again, the value itself would be the y-coordinate of 2. So our minimum value would be 2. But if we want to describe where it happens, we can use function notation and say the minimum value is f of 6, which is 2. Now, when we looked at these graphs, these were what we call the highest and lowest points. And so on this entire graph, what we would actually refer to those 2 points as are what are known as absolute maximum and minimum values. And so when we're looking at the absolute maximum value, this is the fancy mathematical way of saying it. It says that the absolute maximum value of some function on some given domain occurs if f of c is greater than or equal to f of x for all x and d. What that's just really saying is kind of like what we saw on the graph. It's saying that the y-coordinate at some point c is bigger than all of the other y-coordinates in that given domain. That's all that really means. And so if I'm looking at the absolute minimum definition, all they're really telling me is that at some value c, my y-coordinate is lower than all of the other y's in that function at any point in that domain. So that's our fancy definition for that. So we actually, when we found that maximum and minimum value of our graph in that previous example, we were actually finding the absolute maximum of f. And in some textbooks, they'll refer to that as a global max. And we also found the absolute minimum value, or sometimes called a global minimum. And just as extra vocabulary, when we talk about both maximum and minimum values, we call these the extreme values of our function, or sometimes called the extrema. So when I say definitions of absolute extrema, I'm just saying max and min using one fancy word instead of saying both words. Now, it's obvious that we saw those highest and lowest points because on that graph, it really just went up and then came back down, and then that was a boring little graph there. But in this graph to the right, we can see that there's lots of hills and valleys on this curve. And obviously, the lowest point is occurring right here at A. And we would call this guy right here, because it's the lowest point overall, we would call this guy our absolute min. And so our absolute minimum value occurs at A, and our absolute min value would be the f of A value, whatever that happened to be. And then we can see all the way over here at D that this point is our overall highest point. And so we would call this our absolute maximum value. And again, the absolute maximum value would be whatever the value of f of D was. But if we studied just smaller chunks of the graph, let's say we studied only from A to C, all of a sudden that top of this hill right here becomes a maximum. And if we break it up into other sections right here, all of a sudden this little guy right here, he becomes a minimum. So when we have these graphs that have all these different hills and valleys in them, and we want to study just smaller sections of them, what we start looking at is how they are working on an open interval in that domain. So I can break it up, and as long as this point is higher than all of the other points near it, and we use the open interval to kind of represent that nearness, as long as I'm looking at the highest point on a smaller interval of my graph, I can call this a maximum value. But it's not the absolute because it's not the highest of the entire graph. So we call this a local max, or sometimes called a local or a relative max. And then this guy right here, because he's lower than the points near him, he'd become a local min. It's possible that a point can be both an absolute and a local extrema. So in this case right here, because we're kind of in the middle of the graph and it keeps going, it's the absolute maximum, but on a smaller interval right here, it's also a local. So this guy has double personality. It's an absolute max and a local max. And then this right here would be a local min. Now, one thing I want to point out is that when I found these points right here, notice that this endpoint, it's kind of just in the middle of nowhere. And even though he's higher than the points to the left of him, when we were looking for local extrema, they have to be on an open interval, and you have to be able to find points on both sides of it. So endpoints right here cannot be local extrema. They can be absolute extrema if they're at the lowest point on the entire functions graph right here. So this guy is an absolute min, but this guy is not an absolute max because he's not the highest point overall. So endpoints can be absolute max or mins, but they cannot be local extrema. Local extrema can only occur within smaller domains of the overall function. So the next slide here is going to give us that technical definition for local or relative, again, depending on what textbook you're looking at, extrema. And notice that what changes for local extrema is that we're still saying that this function is greater than the y values, but we're not looking at the overall domain of the function here. We're saying when x is near that value. So we're saying that we've got some point C that's higher than some of the points around it and the closest points to it. And so we're looking at really some open interval where C is inside that interval, and you have some points to the left and right of it that would be lower, and that would make this guy go higher and become a local max. Or if we want to go for a minimum, then this y coordinate would be lower when the values for x near that point were a little bit bigger than that. So again, the big change here is that in local extrema, we're talking about the value of x is near where we're saying that this point occurs at. And so we're looking at an open interval that has that point C somewhere in between it. So like I mentioned on the previous slide, local extrema cannot occur at endpoints of a function because they need to be inside an open interval. And as we saw, a point can be classified as both a local and an absolute extrema when they're living within the function itself. All right, so enough vocabulary. Let's go and put it into practice here. So on this graph, I've labeled a couple key points, and we want to see if we can define all of these values here. So the first thing I want to find is an absolute maximum value. And so I want to look at my graph, and this is a closed dot here, and that's a closed dot there. And my absolute maximum would be the highest point altogether, and I can see that's happening right here at this endpoint. So I can say my absolute maximum value is 1, or I can say f of 0 equals 1. And this will tell me when it's occurring and what it actually is. So this occurred when x was 0, y was 1. My absolute minimum value when I'm looking at this curve, the lowest point altogether, is occurring right here at this value of pi negative 1. So my absolute minimum value would be the y-coordinate there, negative 1. And again, if I want to use function notation to show when it's happening, I can say it's happening at pi, and at pi, the function value is negative 1. Now, if I'm looking for a local maximum, this function does not have any local extrema. There is no point on any smaller interval that is higher than all of the guys around it. So again, local extrema cannot occur at endpoints. So this graph actually has no local extrema. But it does have a local minimum because this point is not only the absolute min for this function, but it's also on a smaller domain. If I were to take out a chunk of it, it's the local minimum value for the points near it. So we're going to say that that same value that was our absolute min is also our local minimum value of negative 1. And again, we can define that using function notation if we wanted to. All right, so in this graph, we had some absolute max and min points, and we had a local minimum value, but we didn't get any local maximums. Now in this graph, it's hard to see, but this right here is a vertical asymptote occurring when x is equal to negative 1. So that means that as the graph approaches that value for negative 1, it's going to keep climbing. And it's hard to tell, it didn't print very well, but this was supposed to be an open circle. So I'm going to draw that right here. And so if I make that point right here an open circle, and this has an asymptote here, my absolute max, even though this graph seems to be climbing, and I get to this high point, because of the asymptote, it's going to keep on climbing. So this graph has no absolute maximum value. And it also has no absolute minimum value if I make this point an open dot, because the lowest point here should occur right here, but I've made it an open point, so I never actually equal that value of 4, 1. So since this is an open circle and I never actually equal that lowest coordinate at 1, this would have no absolute minimum value either. And in this case, there's actually no local extrema because the graph doesn't kind of have any hills or valleys in between those two ends. And so we don't get that local extrema because there's no smaller subset where one point is higher or lower than all of the points around it. So these guys, we have none of any of these key characteristics. It's pretty crazy. So the last thing we're going to look at is how we can use extrema to draw a graph. And so we're going to be given some characteristics about a function. And then we're going to just take those characteristics and try to draw a sketch of a graph. Now, one thing I want you to realize is that when you're tasked with drawing a graph, given some characteristics, what I draw and what you draw might be two completely different graphs, but we must meet the criteria here. So if they're saying that we must have an absolute maximum at 0, that means when x is 0, I must have the highest point on my overall graph. And I do see that my domain is closed, so from 0 to 8. So I'm going to just go ahead, and if I want an absolute maximum at 0, I'm going to go ahead and just choose a random spot on here. I'm choosing that height right there at 7. I don't know, it looked good. And that's going to be the highest point of my graph in here. And then it says I want an absolute minimum at 3. So again, that's telling me when x is 3, I want to have an absolute minimum value. And so when x is 3, I want this to be the lowest point anywhere on my graph. So I'm going to just choose, let's go down into the negatives. I'm going to just choose this random point down there. And then it's telling me that I want a local minimum at 7. And so again, it's telling me when x is 7, I want a local minimum to occur. So that means that somewhere at 7, my graph has to dip down and then come back up. And now I'm just going to try to connect the dots to make sure that all of these things happen. So I want an absolute max at 0. So none of my graph is ever going to go higher than this point. And I want an absolute minimum at 3. So my graph is never going to go lower than this. So I'm just going to connect these 2 points. And then to get this to be a local minimum at 7, I'm going to have to kind of climb up and kind of come back down towards it. And then as long as this point doesn't go higher than that right there, I'm going to do that. Now I added an extra characteristic that wasn't provided, but I needed to do that in order to make this guy right here a minimum value at 7. But now I can see my highest point overall was at 0. My lowest point overall was at 3. And then I had a local minimum at 7. My graph dipped down and went back up around that point. So on that open interval, it went to that. And so I created a local min there. So that's one example. And then here we want to create an example of a function that has no local extreme points. So if I want no local extreme points, that means that in between my endpoints, I don't want to have any hills or valleys, because once I create a hill or a valley, that's when I'm going to create an extrema point. So I can have a maximum value or a minimum at 3, and that would become an absolute max or min because it's at the endpoint. And I can do the same thing at 10, have an absolute max or an absolute min at 10. But as long as my graph doesn't wiggle in between those points, I won't create any extreme value. So let's just go ahead and at x is equal to 3, let's make this be an absolute minimum value, and let's choose this random number. And then at 10, let's go ahead and just choose some random high point up here. Again, those are just random points. So these guys would become absolute extrema because they're at the end of my graph on that domain that we're studying. And then as long as I don't make hills or valleys in between here, I won't create extreme points. So I'm just going to kind of just connect these dots and maybe make a slight curve in between them, but I never dipped down low enough to make a minimum, and I never went up high enough to make a maximum. So I have some absolute extrema, but no local extrema. So now that we've looked at a couple different examples and we've looked at all of this vocabulary here, what you're going to do is on page 211 in your textbook, you're going to do problems numbers 3 through 9 and 13. For the odd problems, you can check your answers in the back of your textbook. And then in numbers 7, 9, and 13, you're going to be drawing your own graph similar to my last two examples. So again, you might not exactly get the graph that they provide in the back of the book, but you just want to make sure that your graph has the given characteristics from the original problem there. All right, and when you've finished those problems, you can upload your work to Google Classroom, and then next class we'll be ready to start looking at how we use calculus to find these maximum and minimum values.